Okay, so this is 16.2. In 16.1, we talked about integration, multivariable integration, for example, f of x comma y equals x squared y. But the regions that we worked with were always very, very simple. They were rectangular, or in terms of the three variable situation, they were rectangular boxes. So today we're going to work with more interesting regions. And that's where all the complication comes in when it comes to these kinds of integration problems. So we'll see that setting up these problems is 99% of the work. The rest of it, the actual execution of the integration, is just going to be doing two one-variable calculus integrations, just as in 16.1, with one small new thing where the limits of integration can be a little more complicated. All right, so in the last section, we integrated a to b, c to d, all right? And it was very straightforward in terms of setting up the integral. It was just, for example, if you wanted to do dx dy, x equals a to x equals b, y equals c to y equals d, all right? Okay, so what we're going to do today is we're going to be integrating over more interesting regions. So perhaps a region that looks like that. We want to integrate over something that's not square. Okay, all of today will be two variable. Three variable situation will be a later section. Okay, so let's just jump right in. Let's integrate f of x comma y equals x squared y over the triangle with vertices 0, 0, 1, 0, 1, 3. Oops. Okay, so that's the function we're going to be working with, and the region now is going to be a triangle with these vertices. Okay, so the key to all these problems is you want to draw the region. Always draw the region. All right, it's really, really easy to make mistakes if you do not draw the region. All right, so let's see. We've got a triangle. It's vertices 0, 0. 1, 0 is here. And we got 1, 3 is right there. So this triangle is going to be this guy right here. All right. Okay, so this is 3 right there. Okay, so how are we going to set up this integral? Well, the first thing we want to do is decide whether we want to integrate dy dx or dx dy. Let's do dy dx first. So just as last time, that means we want to be working with vertical integrations first. So let me draw my region again. Here's 1, here's 3. This is my region inside the triangle. So I want to integrate dy dx first. So my function was x squared y. So my integrals, my inner integral, the first integral I'm going to be working with is integrals where y is changing and x is fixed. X is constant, right? So one typical example of such an integral in terms of our picture would be, for example, integrating from here to there, right? And of course, we want to do these kinds of vertical integrals for a range of x's, right, starting from this left-hand side and ending at that right-hand side. And what's going to happen is that will fill up our region with vertical lines, right? And that indicates that we've set up our integral correctly if we set everything up in this way. All right, so let's look at a typical vertical line. So right here, so typical vertical line, we always start at, so if we look at our picture here, we're always starting from y equals 0, and we end up at y equals the line. All right, so y equals 0 to y equals the line. All right. Okay, and let's set up the x as well right now. We need these vertical lines to fill up the entire region. Same idea as from last time where we needed the vertical lines to fill up the entire rectangle. Now it's the entire region. So we start our first vertical line here. And we do vertical lines starting from x equals 0. And our last vertical line is at x equals 1. All right? So that means our limits of integration here are going to be x equals 0 to x equals 1. Okay? All right, so the only thing we have to do now is figure out what y equals the line means. And for that, we need to write down an equation for the line. This point right there is at 1, 3. And that point right there is 0, 0. So this line is a line through the origin. It has slope 3. And so this line is actually y equals 3x. All right. Okay, so that instantly tells us we want to go from y equals 0 to y equals 3x. So this y equals line, we can replace it with x equals 0, x equals 1, y equals 0, y equals 3x, x squared y dy dx. And here's the thing that's a little bit different from what we saw last time. Last time we only had numbers, right, in all our limits of integration, but this time we have actually x's appearing in the limit of integration. But that doesn't matter, because once we actually do this first integral, we're going to plug in values, right? We're going to plug in 0, we're going to plug in 3x, and that'll leave us with x's, which is fine, because our second integral will take care of those x's. All right? Okay, and that's it. So let's actually do this one just to see that we actually get, what we're supposed to get, which is a number, x equals 0, x equals 1. And again, it's always good to write the x equals and y equals just as a kind of safety thing in case you mess something up in terms of the order or something. You write dx, dy by accident, you'll catch it because things are not compatible. All right. Okay, so x squared y dy dx, we're integrating with respect to y first. And so x squared y, the integral, the x squared is constant, so we get 1/2 x squared y squared. We're evaluating that from y equals 0 to y equals 3x, and then we have to integrate dx. All right. And so this ends up being x equals 0, x equals 1, 1/2 x squared. When we plug in y equals 0, we get nothing. When we plug in y equals 3x, we get 3x whole thing squared. And here's the important point. At this point, no more y's in the problem, only x's. Right? So this is just a one variable calculus problem. If you see any y's at this point, you've done something wrong. And also the second point is that 3x up there, right? It's not a problem at all, because at this point that 3x goes to here and we just have a function of x, right? So it's perfectly legit integral at this point. Okay, and the rest of this is purely one variable calculus. X equals 0, x equals 1. Let's pull the 1/2 out. Let's pull the 3 out. X to the 4 dx, right? Something like this. And so we just get 3 over 2, 1/5, x to the 5, x equals 0 to x equals 1, which is going to be 3 over 10. Okay. All right. That's pretty much it with the idea. It feels very simple, but setting up the region, drawing the region, figuring out your limits of integration, that's where a lot of the complications might come in. All right, let's do this example. Doing the other point of view, where we integrate with respect to dx first instead of dy. So remember that we always have this choice when you have multiple variables as to which variable you're integrating first. All right, so we did dy dx first. Now let's do the same integral dx dy. All right, so this is the same function, x squared y, right? But now we're integrating with respect to x first. So we're going x equals something to x equals something. And the outer integral is y equals something to y equals something. All right, if we're doing dx first, it means that our integrals are horizontal, or at least we're going to represent our integrals in terms of a picture as being horizontal, because x is changing and y is constant. So a typical integral will be something like from here to there. All right, it's always going to be from smaller value to bigger value, right? X equals the lower limit of integration is smaller than the upper limit of integration. So we're integrating, when we look at this picture here, 0 is on the left, right? And the positive numbers are on the right. So this number here should be smaller than that. So that should be my lower limit of integration. That guy should be my upper limit of integration. Okay, so we can see the lower limit of integration is the line. Let me just write like that for a bit. And my upper limit of integration is going to be 1. Okay, and we can do a quick check, right? No matter how I draw my horizontal line, no matter where I draw my horizontal line, it's always from this particular line to 1, this particular line to 1, this particular line to 1. All right, so everything is consistent. Okay, for the dy part, we want to think of this as filling up our region with horizontal lines, right? And how do we do that? Well, we start our first horizontal line right there at y equals 0. And in order to fill it all up, right, we go y equals a little bigger, all the way up until we get all the way up to y equals 3. All right? So that means that the y limits of integration is going to be 0 to 3. Okay. All right. In terms of the equation for the line, right, if we want to fill that in, well, the line here, it was a line of slope 3 at the origin, so we had y equals 3x. But what we want is x equals, right, something. So what we do is we take this equation here, y equals 3x, and convert it into something in terms of x equals something, right? So y equals 3x is, of course, the same as x equals 1/3 y. And so that's obviously the same line. So x equals, this line here, should be 1/3 y. Okay? And so ultimately the integral that we compute with is y equals 0, y equals 3, x equals 1/3 y, x equals 1, x squared y dx dy. Okay? All right, so the important thing is, if you look at this integral, right, it looks very, very different from the y integral, from the dy dx integral. So the dy dx integral, we went from y equals 0 to 3x, and then x equals 0 to 1. But now we're going from x equals something complicated as the lower limit of integration to x equals 1, and a y equals 0 to 3. So the numbers are completely different. All right? So you do not want to, let's say you've set up the dy dx integral, if you want to decide for whatever reason to do dx dy, you don't want to just directly translate it by swapping the limits of integration or anything like that, right? If I just swap these two guys and thinking that I get a dy dx integral, I'm going to be in big trouble, because then my outside integral is going to be an integral that involves y, and my final answer is not going to be a number. Okay, so if you do, for example, want to set up an integral both ways, then always refer to the picture for both ways. All right, so here I did not use my dy dx integral formula here to help me get my dx dy integral. All right, so just set it up from scratch from the picture, okay, by drawing the lines, the appropriate either vertical lines for dy dx or the horizontal lines for vertical lines dy dx, horizontal lines dx dy. All right. Okay, so of course, if we actually sat down and did this integral, we would get the same answer. And again, just a very quick check. When we do this integral in here, we're going to end up plugging in, since it's a dx integral, we're going to end up plugging in values of x. And so when we plug in x equals 1/3 y, all the x's will disappear from the problem. And so our outer integral is going to be perfectly fine. Okay. All right, so roughly, this section is just going to be a lot of examples of how to set up when you have various different shapes of regions or different kinds of regions. There will be one very interesting section where we want to learn how to switch the order of integration. But outside of that, it's mostly an example-based section. All right, so let's integrate f of x comma y. And this time I'm not even going to bother writing down the function. Again, like we said, the key is to set up the integral, and the rest of it is just total brutal integration calculation. All right. Okay, so let's just set this up. Integrate f of x comma y over the region. Bounded by let's say y equals x cubed and y equals 8x squared. Okay. All right, so as usual, we always want to draw a picture. Okay, so let's see, y equals x cubed, that looks something like this. Oops, that's terrible. Right, it has a flat horizontal here. And I should label this y equals x cubed, and y equals and y equals x squared is going to look something like that, or 8x squared rather. Okay, x cubed lives under y equals 8x squared from 0 to, this would be 2 here, right? Why is it 2? Well, when you plug in 2, you get y equals 2 cubed, which is 8. And actually, I want this to be, sorry about this, I want this to be 2x squared. All right, so if you plug in 2, you get y equals 8 as your output for the y equals x cubed. And when you plug in y equals 2, you get y equals 2 times 4, which is 8. So that's the intersection point. They also intersect at 0, 0. And so that tells me the region is going to be everything between 0 and 2, kind of this wedge right there. Okay. All right, this one I guess was kind of easy to see, but if it was a more complicated formula, essentially what I did was I wanted to figure out this intersection point. So I said they have this at this intersection point, I have y equals x cubed and y equals 2x squared. So I solve these two equations simultaneously, which means that x cubed equals 2x squared, which means that x equals 0, and x equals, canceling out the x squared, if x is not 0, that means x is equal to 2. All right. And so actually it gives me, of course, it gives me both these points. Okay, and you have to recognize that, of course, y equals x cubed lives underneath y equals 2x squared over this region to get kind of an accurate picture. And that's certainly true because, well, when you take x cubed for these smaller numbers, you're going to get numbers. For example, I guess, x equals 1. X cubed is going to be at 1, and y equals 2x squared is going to be at 2. All right. All right. Make sure you know which guy is above the other, because when we do our limits of integration, right, it's going to matter in terms of which limit of integration is going to be above the other. Okay, so let's set up our integral. And again, this is always the key part, right? Having a picture and then setting up the integral is going to be very straightforward once we do have the picture. So let's decide to do dy dx first, for example. Let me draw just the relevant parts of the picture this time. So this is y equals 2x squared. This one is y equals x cubed. If we want to do dy dx, so we want to integrate with respect to y first, then we're going from y equals something to y equals something, and then x equals something to x equals something, right? Our integrals with respect to y are vertical integrals, right? Y is the one that's changing, so we represent it with vertical lines. And we can see if we want to fill this region up with vertical lines, it's consistently always, the vertical lines consistently always start at x cubed, and they always end at 2x squared. So that means we go from y equals x cubed to y equals 2x squared. All right. Okay, if we do want to fill this up with vertical lines, we need to start our first vertical line at 0, right? And then we want to do vertical lines all the way until we get to this intersection point right there, which we said was 2, right? So x equals 0 to x equals 2. All right. And that's it. That's our setup. And now we just plug in whatever function we have. We do our integral. This time, both limits of integration are functions having to do with x. But again, it doesn't matter because once we plug those in, right, after we've integrated f, we're going to get a function of x, which is just going to integrate away to a number once we've done the outside integral. Okay, if we wanted to do the other integral first, dx dy, then we would represent our integral with a horizontal line. And our horizontal lines, if we want to fill this region up with horizontal lines, they would always start here and always end there, right? X equals smaller value to bigger value, of course, as usual. Smaller value to bigger, smaller value to bigger. And we can see it always starts at 2x squared, or starts at the parabola and ends at the cubic. All right. Okay, so that means our integral is going to be integral from the parabola up to the cubic. Okay, but this time, of course, we need x equals, right? And what we have here is our formula in terms of y, so we just translate that. Our parabola, y equals 2x squared, is the same as x equals square root y over 2, right? And our cubic is the same as x equals cube root of y. Okay, so we're starting from the parabola, so x equals square root y over 2, and we're ending up at cube root of y. All right. Okay, of course, when I took the square roots, technically I should have popped out a plus or minus, but of course everything here is happening in the first quadrant, so I know I can toss away the plus. Okay. For the dy part, I want to fill this whole region up with horizontal lines. My first horizontal line lives here, right? And then I'm going to do horizontal lines all the way up until I get to that point right there. Okay, so I'm going to do horizontal lines from here all the way up to there. Okay, what is that? Well, that's the y output I get when I put in the input x equals 2. Okay, and so, right, y is equal to x cubed, so when I put in 2, I get 2 cubed out, so that's going to be 8. So this integral is going to be from 0 to 8. All right. Okay, and again, from here, you just do your calculations. When you do plug in, just a quick look, right, when I do plug in, after doing the dx integral, I'm no longer going to have x's because all the x's are going to be replaced by y's. All right. And again, notice that the limits of integration look very, very different from one order of integration to the other, right? 0 to 8 versus 0 to 2. You're integrating to 2x squared from x cubed to 2x squared, and down here, you're going from square root to a cube root. Okay, so again, don't try to translate the integral directly. Always refer back to the picture. Okay. All right, let's set up, find the volume of a sphere of radius 3 about the origin. Okay, so we've got a sphere about the origin. We want to set up an integral that represents its volume. And again, this is a sphere, so let's kind of make our lives a little easier. Let's only do the upper hemisphere, and then we'll double our answer. Well, we're not actually going to calculate it, but that's what we would do. All right, so let's, so volume is going to be 2 times this integral here. All right, so just the upper hemisphere. Okay, that makes our lives a little easier here. Let's see. So our function is going to be, well, the sphere of radius 3 about the origin is x squared plus y squared plus z squared equals 9, right? So the function we want to be talking about is, naturally it's going to be in terms of z. So we're talking about z equals 9 minus x squared minus y squared square root. And we're taking a positive square root because we want to integrate under the upper hemisphere, okay? So this is going to be, this guy is going to give me my function, all right? So my f of x, the function I want to integrate, is going to be, let me move this v equals 2 down to here. So the function I want to integrate is going to be this guy here. And essentially, if you think about how you integrated to find, or how you can set up an integral to find the area of a circle of radius 3, about the origin in one variable calculus is pretty much going to be exactly the same idea, and the numbers or the quantities will look very, very similar. Okay, what is the region of integration? Well, we only want to capture the, well, this function is actually only defined inside a circle of radius 3. So we want to integrate inside that region right there, circle of radius 3. And so our region of integration is going to be a circle of radius 3. All right. Okay. And we'll say these words quite a bit. What is the region of integration that you want to work with? Think of the sun as shining from above the z-axis, let's say. So we have the sun shining like this. The shadow that the object that you're kind of working with, the shadow that it makes on the xy plane, that's the region that you want to integrate on. Okay, for this particular problem, it's very straightforward, but we'll definitely get into examples where it's not as obvious. So this kind of idea of the shadow is good to always keep in mind. And again, in this example, this is the shadow, and that's the region I want to integrate over. Okay, circle of radius 3. So if I want to do an integral, let's say dy dx, so this is going to be double integral of square root 9 minus x squared minus y squared, let's say dy dx, right? This is going to be y equals something to y equals something, x equals something to x equals something. So I'm going to be integrating from vertically, y equals, right, first, dy dx. So my integral is always going to start down here, the lower semicircle, and I'm going to go all the way up until I hit the upper semicircle. And the whole, if I do fill this region up with vertical lines, it's always consistent, always from the lower semicircle to the upper semicircle, lower semicircle to the upper semicircle. Okay, so I just need equations for each of those semicircles. The lower semicircle is, so this is a circle of radius 3 about the origin. So the lower semicircle is going to be, so the circle is x squared plus y squared equals 1. I want it in terms of y, because I want y equals something, right? And so I can rewrite that as y equals square root 1 minus x squared as the upper semicircle, and y equals minus square root, equals 9, right? Circle of radius 3. 9 minus x squared as the lower semicircle, upper semicircle, and lower semicircle. Okay, and again, we wrote it in terms of y because we wanted we decided to do dy first. Okay, and so now our limits of integration are going to be y equals minus square root 9 minus x squared to positive square root 9 minus x squared. And then what about x? Well, we need to fill this region up with vertical lines. We want to start on the left and fill it up all the way until we get to this point on the right. Okay, this is a circle of radius 3, so this point on the left is x equals minus 3. The point on the right is x equals positive 3, so x equals minus 3 to positive 3. Okay, so this is one way to set this integral up. This particular one is not going to be easy to integrate, but the next section will allow us to integrate these things very easily. All right, next example. So again, essentially this section is example after example of, in a way, more and more complex, complicated situations. So let's find the volume between the upside down paraboloid, z equals 9 minus x squared minus y squared, and the plane, the plane 3x plus 2y plus z equals 1. All right, so this guy is a paraboloid, upside down. So you definitely want to be able to recognize what these equations represent, because otherwise you're not going to be able to visualize what you're integrating. And then if you can't visualize what you're integrating, you're not going to be able to visualize the region of integration, and then you won't be able to set up the integral. So this is an upside down paraboloid. And this one is a plane. Okay. So essentially, our picture is going to look something like we have an upside down paraboloid like that, right? 9 minus x squared minus y squared. That means its height is at 9. And we're cutting it with a plane. Maybe let's represent it like that, right? And the cut is going to be a region that looks like this, kind of. And we're integrating, we're calculating the volume inside here. All right. Okay. So of course we have to recognize that, for example, the plane lives underneath the tip of this vertex, of course. Otherwise there wouldn't be a region to integrate. Okay, and that does happen because, for example, when, like we said, the vertex is at 9 because when x and y are 0, z is equal to 9. But when x or y are 0 for the plane, z is equal to 1. All right, so this cut point where the plane cuts the paraboloid, that happens right there at 1. Okay. Okay, so this one is a lot more difficult to set up because, well, first of all, our region is quite complicated, but also it's not that easy to visualize what our region is, our region of integration is. But again, we want to take the point of view that we have the sun shining from the z-axis, right, vertically downwards, and whatever the shadow of our region is down here, that's going to be the region of integration. Okay. All right. So if we think about this particular picture, the shadow is going to be determined by this curve right there. Oh, that was a bad color. Let's use this. Is going to be determined by this guy right there. All right. There's not going to be anything. The sun to the kind of to the left here is going to shine right through. Right. The sun to the right is going to shine right through. But everything inside between inside this kind of intersection region is going to be blocked by the by our region. All right. In terms of the sun shining downwards, and so whatever the shadow of this guy is, right, that's going to determine the boundary of my region. Okay, so again, this is why you need to be able to visualize the pictures. And I think a good idea when doing the online homework especially is they often give you the picture or they often walk you through these problems step by step. I think it's a good idea when they tell you the problem, just try to do it straight out without going through their ABCDs so that you get used to working the problem yourself and knowing all the steps yourself, all right, instead of being walked through them every time. Okay, and of course try to draw the picture yourself instead of looking at perhaps the picture that they have, if you can, all right? Okay, so we've concluded that we want to figure out kind of what that blue intersection is, and that's what it is. It's the intersection of the plane with the paraboloid. And so, well, if it's the intersection, that means that that's going to be given by z equals 9 minus x squared minus y squared and 3x plus 2y plus z equals 1 simultaneously, right? And so we can solve this for the region of for this blue curve. Okay, so let's see. We want everything in terms of x and y, of course, right? Because our region lives on the xy plane, right? The shadow is something that lives on the xy plane, so there should be no z's in it, right? So we want to get rid of these z's. Okay, so if z is equal to 9 minus x squared minus y squared, that tells me that 3x plus 2y plus 9 minus x squared minus y squared should be 1, right? And that already gives me a great idea for what this should be. So Let me throw some of these things to the other side so that these guys are positive. So this is x squared minus 3x. Let me write it as plus y squared minus 2y is equal to 8. All right. And so this guy here represents the shadow, this shadow region down here, represents the equations that describe this guy down here. All right. So again, that's the boundary of the region over which we want to integrate. Okay. So essentially, if we can figure out what this thing is, we know what our region is. Okay. Okay. So what is this? Well, we have x squared, we have y squared, we have x and y's here. So we're just going to complete the squares for both of these, and and this is going to be a circle of a certain radius about some point, not the origin, right? So this is going to be, this is going to be x squared minus 2 times 3 over 2x plus 9 over 4 minus 9 over 4, completing the square to get my x's. Plus, and then let's complete the square for the y's. That's just going to be y squared minus 2y plus 1 minus 1. That whole thing should be, let me put the plus over here. That whole thing should be equal to 8. These three guys go together. These three guys go together. And we end up with x squared, x minus 3 over 2, which was the point of the completing the square, squared, plus y minus 1, whole thing squared, equals 8 plus 9 over 4 plus 1. Okay, so that's equal to 9 plus 9 over 4, which is 45 over 4. Okay, so ultimately, we have a circle of radius 45 over 4 square root of that. Its center is 3/2, comma 1. All right. So 1, 2, 3. So 3/2 lives here. 1 lives here. All right. We've got a circle of radius. Let's see. Square root 45 over 4. So it's going to be something like that. Okay. All right. So for example, if we want to integrate horizontally, let's say this time, then we see we always go from the left-hand semicircle. So here's kind of our delineator of our semicircles. From the left-hand semicircle to the right-hand semicircle, right? And it's consistent in that way, always from the left-hand semicircle to the right-hand semicircle. And so our limits of integration are going to be from, well, if this is our equation of our circle, dx dy, we're doing dx first, so x equals something, y equals something to y equals something. We want our semicircles described as x equals something. So we just solve for our x's from our equation of our circle. So we get x minus 3 over 2 is equal to square root 45 over 4 minus y minus 1 squared, plus or minus, all right? And so we get x equals 3/2 plus or minus square root 45 over 4 minus y minus 1 squared, right? The 3/2 minus represents the left-hand semicircle. The 3/2 plus represents the right-hand semicircle. And so our integration is going to be 3/2 minus square root 45 over 4 minus y minus 1, whole thing squared, to 3/2 plus, same thing. All right. And then in order to fill this region up with horizontal lines, we got to start from the bottom here, go all the way up, right, until we get to the tip of the circle. Okay, what are the coordinates of these points? Well, our center here is at 3/2, comma 1. So there's our, let's do it here. There's our center, right? Our radius is root, so this is at height 1. Because y equals 1 gives me my y coordinate of the circle. Our radius is square root 45 over 4. So our lower point right here is going to be 1 minus that. So this is going to be 1 minus, 1 minus square root 45 over 4. And our upper one is going to be 1 plus our radius. Okay. Okay, now what about the function? Well, let me draw the picture again. So we were integrating the region that was below the paraboloid and above the plane, right? And so just like in one variable calculus, when you wanted to find the area between two curves, right, if this was f and let's say this was g, right, we found the intersection points. That gave us our limits of integration. That's essentially what we just did with all our calculations right now to find our limits of integration. Okay, and notice that it's actually the same procedure as you did in one variable calculus, right? To get this left limit of integration, you had to find the intersection of f and g. To get the right one, you had to find the intersection of f and g. And that's exactly what we did when we equated all the way up here. When we did this right here, that was finding the intersection of our two graphs, right? Right there. And so it's pretty much the same idea, of course, far more complicated because we're in a two variable setting. Okay, in any case, when we did that in one variable calculus, if we decided this was a to b, then we integrated from a to b, and then we just subtracted. Let me make this a little more obvious here. This is f on top, this is g on the bottom. To get the area between them, that's essentially the area under the top one minus the area under the bottom one, right? So f minus g. Okay, so now it's literally the same idea. The top one is the paraboloid, so its equation was 9 minus x squared minus y squared. And then the bottom one is was the plane, and so we subtract that. 3x minus, plus 2y. I want to write it in terms of z, right? So that's z equals 1 minus 3x minus 2y. And then this was dx dy. Okay. So this guy here plays the role of my f from my one variable calculus picture, and this guy plays the role of my g in my one variable calculus picture. And again, those equations come from the z equals, right? Z equals this, z equals, throw everything to the other side, 1 minus 3x minus 2y. And that gives us that. All right, and then the rest of the problem is just brutal integration. This one is going to be pretty horrible. But that's, again, just an integration problem, right? All the kind of new multivariable calculus work has already been done at this point. Okay, our next example, let's phrase our next example in terms of area. So let's find the area of the region in the first quadrant. So this is an area. So this is going to be, this lives in the plane, right? So this area in the first quadrant bounded by y equals x squared. Y equals x squared. Y equals 4x plus 12, so that's a line. Y equals x squared is a parabola. And y equals 12 minus x. Okay. All right, so again, we need to draw this region. And then because we're finding the area of a region, essentially our integral is going to be double integral dA over our region of 1. Okay, so that's going to be area. Okay, this is equivalent to, in a way, if you want to find in one variable, there's not really a good one variable calculus equivalent, because in one variable calculus, this would be like saying, find the length of the interval from a to b, right? And what is that? That would be integral a to b of 1 dx. Okay, because you'd be looking at everything under a height of 1. And so that area is just going to be b minus a times the height of 1. All right. And so it's the same idea here. So if we have a function whose height is 1, then when we integrate over whatever region, we're going to pop out the area of that region. Okay. So let's do this. Again, you can obviously, this is actually, you did this kind of problem in one variable calculus, but we're going to set it up as a 2-variable calculus double integral. Okay, so what is our region? Again, as usual, we always need to draw a region so that we can get our limits of integration correct. And for this particular problem, we'll see especially why we want to draw the region. All right, so let's see. So this region, we've got y equals x squared, that's a parabola. We're only interested in the first quadrant, so I'm only going to draw the left-hand side here, y equals x squared, x squared. Our second one is a line with a positive slope. Its y-intercept is 12, so 12 right there, positive slope. All right, and there's no need to be really super accurate about the pictures in terms of like having to do it to scale or anything, so not going to worry about that. 4x plus 12. Our other line is going to be a line that has negative slope. Its slope is -1 actually. Its y-intercept is 12, so it's going to be something like this. Okay, and so our region is the region bounded by all these 3 curves, and so that's going to be this guy right here. Okay. All right. So here we can see that our integrals are going to be a little more complicated than the ones we've seen up to now, because let's say we want to do dy first, right? So if we do dy first, let me write this out, dy dx, and again, we're just integrating the function 1. All right, it's going to be y equals something to y equals something, x equals something to x equals something. Represent it with vertical lines, and so our integrals are going to go from here to there, right? From here to there, from line 12 minus x to line 4x plus 2, except it's not consistently that way, right? Once we get to past this kind of intersection point, we're actually integrating from the parabola up to the line. Okay, so there's a parabola to line, and this one is line to line. So immediately we see that we're going to have to do, we're going to have to set this up as the sum of 2 integrals. The first integral is going to be, at least in terms of the picture representation, it's going to be vertical lines going from the lower line to the upper line all the way up to here. Okay, and then once we're past here, we transition to vertical lines, still vertical lines of course, because we're still doing dy, but they're going to be going from the parabola to the line. Okay, so this one, there's no escaping it. Actually, it's going to turn out there's no escaping it either way, whether we do vertical or horizontal. But we're doing it vertical, there's no escaping that we're going to have to do 2 integrals. So y equals something to y equals something. Oops. 1 dy dx, x equals x equals. All right. All right, so for the first one, it's going to be from the first portion of this integral. It's going to be from the lower line to the upper line, right? So that's going to be y equals 12 minus x to y equals 4x plus 2. Okay. In order to fill up this first region with vertical lines, we're going to start at x equals this left-hand side right there, x equals 0. And we're going to go all the way until we can see we get to the intersection of the lower line and the parabola. Okay, so x equals 0 to x equals that point. All right, or if I just draw it on the x-axis, it's going to be x equals that guy right there. Okay, and again, that's the intersection of the lower line with the parabola. So that's going to be, well, the parabola is y equals x squared. The lower line is y equals 12 minus x. So I need, the intersection is going to have the same y and the same x. So x squared has to be 12 minus x. All right, and so x squared plus x minus 12 is going to have to be 0. And so x plus 4, x minus 3 is going to be 0. And so x is equal to 3, right? X equals minus 4 we don't want because that doesn't live in the first quadrant. All right, so that point right there is x equals 3. right? So we go from 0 to 3 for our first integral. Okay, our second integral is going to go from, like we said, the parabola up to the upper line. The parabola is x squared, so y equals x squared. The upper line is 4x plus 2. We start our vertical lines where we left off, so that's at x equals 3. And we end up at, if you do these vertical lines, you stop your last vertical line is going to be where the upper line intersects the parabola. So right there, right? And that location is going to be where y equals x squared and y equals 4x plus 2. So that means x squared should be equal to 4x plus 2. Oops. And we just solve that. X squared minus 4x minus 2 equals 0. Sorry, 4x plus 12, right? Yeah, 4x plus 12. Sorry about that. So let's see, where did I have 4x plus 2? Here we go. 4x plus 12. 4x plus 12. Okay, so that's a 12 there. I just miswrote the equation of that line, minus 12. All right. Okay, and then, you know, we figure out what this is. So this is x minus 6, x plus 2, right? And so x is equal to 6, x equals minus 2, but we don't want that one. It's not in the first quadrant. So we end up at x equals 6. So this guy here is at 6, x equals 6. Okay. All right, and that's it. That's our setup. If we integrate these two integrals, we add them up, that's going to be the area underneath this particular graph. Or, sorry, area of this particular region. Okay, notice here, if we wanted to integrate, let me draw the picture again. If we wanted to integrate 4x plus 12, this one is y equals 1 minus x, and we have our parabola. If we wanted to integrate horizontally, we would actually see the same issue. We would integrate, our integrals would be represented by horizontal lines. And down here in the lower part, our horizontal lines are going to go from the lower line to the parabola. And it's going to be like that all the way up until we get to here. And then our horizontal lines are going to be from the upper line to the parabola. So we're going to have to break this guy up into two integrals. Okay. The transition point is going to be happening this time at 12. Okay. All right. For the dy portion of the integral, we're going to be starting the horizontal lines at this location right there, right? And we found that that was at x equals 3. Oops. So this was at x equals 3. And when I plug in x equals 3, this is 12 minus x. When I plug in x equals 3, this guy here is 9, right? And then for the second integral, that was 6. And when x is 6, I'm going to get 36 up here. Okay. So my integral is going to be double integral. I'm doing horizontal, so dx dy. I'm integrating just a function 1. X equals from the lower line to the parabola. So this is going to be x equals, y is 12 minus x, so x is equals y minus 12. And the parabola is x equals square root y, right? And like we said, y equals 9 to y equals 12. So that covers all this lower portion, right, from 9 all the way up to 12. So this region here. And then for the second integral, we're going to be doing 1 dx dy. X equals the line. So our line is y equals 4x plus 12. So 4x is y minus 12. So x is equal to 1/4 y minus 3. right? And our upper limit of integration was x equals still the parabola, square root y. And again, it's positive square root y because we're looking at the right side of the parabola in the first quadrant. And this is going to be y equals, like we said, we want to start this time at 12 with our horizontal lines. And we want to go all the way up until we get to this intersection point, which we said was at 36. So 12 to 36. All right. Okay, and again, if you look at our two formulations of this area, the dy dx and the dx dy, they look very, very different. The numbers all look very, very different. Again, don't try to derive one from the other. Just start from the picture again and then draw the horizontal or vertical lines. It'll help you out quite a bit in terms of figuring out your limits of integration. Okay, so let's do another kind of problem. So this is the kind of new type of problem that we haven't seen before, because in one variable calculus it just didn't exist. And this is the type of problem where you want to swap the limits of integration. So this is an interesting technique. So one of the kind of most typical examples is something like this. You're given an integral, let's say 0 to 1, y to 1, e to the x squared dx dy. All right. Okay. And you're asked to compute it. Okay. The problem is, well, first of all, oftentimes you'll see things written like this. I always like to stick it in. This is x equals x equals. That's y equals, just to always remind me, what's going on. But anyways, if we want to integrate this, we're going to run into a problem because integrating this guy in here is not very easy because it's an e to the x squared. We can't do substitution because we don't have an x down here downstairs to help us with the substitution, right? So one option in terms of double integration is sometimes the integral will be easier if we did dy first and then we did dx. All right. This is exactly that kind of situation. So let me say, we suspect that for this particular problem because if we integrate e to the x squared with respect to y first, there's no y's in the problem. So we know we're going to pop out a y, right? And we hope that that y is going to become something like an x once we plug in the limits of integration. And that will help us in terms of substitution. All right, so that's kind of the idea. And we kind of, in a way, expect that to be true because we see an x equals y here. All right, so we know that that y will likely become something like an x. All right. All right, we're never exactly sure that it's gonna work until we actually do it because there is this x equals 1 up here that might perhaps cause problems. We're not sure at this moment. It's just something to try, right? So let's actually try it. So we're going to swap the order of integration from dx dy to dy dx. And again, we never want to do it straight from here. We want to draw the region first. So the reason I wrote the x equals y to x equals 1, y equals 0 to y equals 1 makes it easier for me to draw the picture. So this problem, as they've given me, I'm doing dx first and then dy. So I'm integrating with respect to horizontal lines, right? And then I'm doing a vertical collection of horizontal lines. Okay. All right. So perhaps it's in this case easier to start out with the outer one. So our horizontal lines will start at 0 and will end at 1. All right. So our horizontal lines will be in between these two, in between this region here. Okay. All right. Now our horizontal lines are going to go from x equals y. So that's just the diagonal line right here. And they're going to, the horizontal line is going to start at x equals y. It's going to end at x equals 1, right? So x equals 1 is a vertical line. Okay. X equals 1 is a vertical line and happens to look like this with the intersection point right there. All right. Okay. Because when you plug in x equals 1, then when x equals y, you get 1, y equals 1. All right. So our horizontal lines are actually going to look, right, from the line to the vertical x equals 1. So from the line to the vertical x equals 1. Okay. And our dx integrals, our horizontal line integrals, are always going to go from this line to there, this line to there, this line to there. Okay. We start at y equals 0. So we start here, we go to there, and we do all these horizontal lines until we get to the top right there. Okay, so this reproduces my region. I know my region is this particular triangle down here. Okay, if you didn't do this, then you could easily have made the mistake to think that the region was perhaps this triangle up here, which it's not. Okay. Okay. In any case, once we have the region, now we can just go from the region to the integral dy dx integral, right? So from here, it's essentially just a problem of the type that we have been doing, right? So vertical lines now, dy dx, y equals something, y equals something, x equals something, x equals something. Doing vertical lines, we start at y equals, well, if we want to fill this triangular region up with vertical lines, they're always going to start at the ground, right? So y equals 0, and go all the way up until we hit the line. Okay, so y equals 0 to y equals the line. The line is x equals y, which is y equals x. So we're going to go from 0 to x. Okay, and where do these vertical lines range from? Well, if we want to cover this entire region, this entire triangle with vertical lines, we need to start at x equals 0, and we need to do a vertical line until we get to x equals 1. So x equals 0 to x equals 1. All right. Okay, and our hope, again, is that this integral will be easier to do than our previous integral. And it looks like it's going to work out because if I actually do this, right, the inner integral, there's no y's, like we said. So this is actually just going to be y e to the x squared, evaluated from y equals 0 to y equals x dx. And so that's going to be x equals 0 to x equals 1. Evaluated as 0 just goes away. Evaluated at x, I get x e to the x squared dx. And this is why we wanted to do this, try this technique, because this guy we can do substitution, right? U equals x squared, du equals 2x dx, right? And so this integral is going to be 1/2 e to the u du, right? When x is equal to 0, u is equal to 0. When x is equal to 1, u is equal to 1. We're only integrating for positive values of x, so this u equals x squared is not going to cause us any problems. And so we're all set. So this is 1/2 e to the u, 0 to 1. And so this is 1/2 e to the 1 minus e to the 0, which is 1/2 e minus 1. Okay, so again, this is something that you wouldn't have been able to do if you had just integrated it directly, dx dy. Right? We wouldn't have had such a nice, simple substitution over here. Okay, let's do one more example of this. Let's do a double integral. Y equals, let's say, x to... let me do this. Square root x to y equals 2. X equals 0 to x equals 4. And again, I'm just going to do the setup, the swapping of the integration part. I'm not going to actually do the integral. So whatever this function is, I'm not even going to bother with it. Dy dx. And the idea is I want to swap the integral. Okay, for whatever reason, right? Maybe this, again, this guy in here looks terrible in terms of integrating with respect to dy. So I want to try it the other way, integrate with respect to dx instead, first. Okay, so if I wanted to do that, I want to draw the region. This region, I'm integrating with respect to dy first right now. So they're vertical lines, and the vertical lines are going to range from 0 to 4. All right, so x equals 0, x equals 4. My vertical lines are going to live between here and here. Okay, my vertical lines are going to start from y equals root x, which looks like this. And they're going to end at the height y equals 2, right? And actually, when I have y equals 2, that's going to intersect with this vertical line right there. Right. So what I see is my region. Did I use? Sorry. Okay. My region is going to be my integrals. Each of my dy integrals is going to be from the square root to the constant, square root to the constant, square root to the constant, square root to the constant. Okay. And I'm ranging from 0 to 4. So horizontal line, vertical line from here all the way until I get to there, until I get to 4. So my region is this upper part, part of this picture. Okay, and again, from here, I'm all set. Once I've drawn the picture, I want to switch it to dx dy, right? Whatever function it happens to be. X equals something, y equals something, y equals something, right? And now I can see I want to start to fill this up with horizontal lines. I start from x equals 0 until I get to the curve. 0 to the curve, 0 to the curve, always. So 0, 0 to the curve. And what's the curve? Well, if y is equal to square root x is equal to y squared. All right. Okay, in order to fill this up with these horizontal lines, I need to start at y equals 0 with my first, there's my first horizontal line, and all the way up until I get to 2. So y equals 0 to 2. Okay, and that's my setup. And again, I hope and pray that this second integral will be easier than my first integral. Okay, so it's always something that you want to keep in mind, this technique. If you see that your original setup is too hard, or the original integral that they gave you is too hard. All right. Okay, so we'll end this with just something maybe for you to think about a little bit. So we've tried to keep the integrals relatively, the regions relatively straightforward. But let's say, but things can become quite complicated. For example, let's integrate or find a volume, let's say. Of the tetrahedron. With vertices, let's say 4, 0, 0, 0, 0, 0, 0, 3, 0, and let's say 2, 2, 10. Okay. All right. In terms of a 3D picture, x, y, z, we're at 4, 0, 0, 0, 0, 0, 0, 3, 0, and 2, 2, 10 is maybe somewhere up here, right? So we've got tetrahedron that looks something like this. Okay, so we want to find the volume of this. This vertex lives above there, like that. So if we want to find the volume of this, we can see that this one is going to be quite complicated because when we do our integral, each of these panels have a different equation, right? We'll have a different equation because they're defined by different planes, right? So this panel right here that's facing us is going to have one equation determined by, let's see, 0, 3, 0, 4, 0, 0, and 2, 2, 10, right? We're going to have another panel on this other side right there, right? That's going to be defined by 0, 0, 0, 4, 0, 0, and 2, 2, 10, right? And then there's another panel on the other side, which is going to be determined by another 3 points. Okay, so this is a good problem to think about to see if you can set it up, because it is kind of a combo of a lot of the examples that we've seen, and it's going to be a little bit of a mess, but it's a good exercise because also, right, you have to figure out what the equation of each of these panels are, right? Just from having only points. And of course, the idea is that each of these panels are planes. You have points on the plane, so you can figure out the equation of the plane by using the point and the normal, and then using the stuff from the very first chapter that we worked on. All right, so this is a good kind of combo problem. In any case, the way you would kind of think this through perhaps is in the xy plane, right? Your region of integration is going to be an xy plane. You're going to have this line segment right there, defined by that guy right there. Another interesting point is where this vertex, the shadow of it, where is it on the ground? So it's going to be right there. Okay, and so you can see the delineations of where to integrate are going to depend on this, and that. Okay, so one of the panels is going to be, this kind of front-facing panel is going to be integrated over that region, right? This side panel here, I should label this X and Y, right? This side panel is going to be that one right there. And this last side panel that we haven't really talked about is going to be that part right there. So you're going to have to break this guy up into 3 different integrals, where each integral is integral of a different function, and those functions are the equations of those 3 planes. All right. And if you look at this a little carefully, when you actually go about doing those integrals, let's see. So this yellow panel here, you're going to have to break it up into 2 integrals, whether you do a dy dx or dx dy. This purple panel on the left is going to be, you could do it if you did dy first and then dx, you can just do a single integral. And this cyanish panel down here, if you did it from here to here, you only need to do 1 integral. All right. So altogether, it looks like the most efficient way to set this up would be 1, 2, 3, 4 integrals. Again, 2 integrals here. Okay. So a nice, interesting problem to try to set up, where it puts together a lot of the stuff that we've worked on in this class. Okay. So the next section, we're going to get more into integration. Well, this entire chapter is integration, and we're going to be just going through all the different kinds of integration that we can be doing. Polar, triple integrals, cylindrical, spherical coordinates, and then general change of coordinates.